I'll frame the problem. So really we were interested in looking at understanding the interaction between groundwater recharge and snowmelt in mountain watersheds. And this was particularly of interest because the majority of snow groundwater studies have been done in high elevation sites in the continental US, so in a very dry, high elevation snowpack. And those snowpacks happen to be less at risk of disappearing due to increased temperatures that are associated with climate warming. So we were wondering if we instead look at groundwater recharge in a maritime climate, so like out here in the Pacific Northwest, if we could see any sort of signal if we compare these groundwater recharges in the maritime climate versus the continental climate. If it's changing to rain, would that, because of climate change, would that be a problem? And so we used several data sources. So I'll actually jump over to the notebooks now, hopefully. So our team was really kind of at several different levels of experience coming into Hack Week. So a lot of people were trying to get just oriented with using Python and Jupyter Hub in general. So we thought a really good place to start was this mashup script that Emilio shared with us the first day. And so we were going to look at these water budget components at two sites in Clackamas, Oregon, and then the upper South Platte in Colorado. We ended up only looking at Oregon because of time, and then I'll also go into a couple other details of why that got complicated. But we used a whole bunch of different data going into this. So there were the sources that Emilio, of course, had originally, and then we also included USGS groundwater data, as well as SNOTEL SWE data to look at. This part, one of the other group members was supposed to get back right about now, but so I'm not exactly sure of a narrative, but I'll try. Okay, well, the beginning of this is fairly similar to Emilio's script, but one of the hardest things that one of the biggest challenges for us was finding a well site, a USGS well site that had daily data. And so to do that, we had a couple different methods. And we used the quasi interface to look for them, but we also use this script here that you can look at the watersheds for the US and then select by state and specific watershed. So we ended up, one of my goals for this week was to use Prajjwal, which is a Python tool that's created by USGS members. And it's specifically for discharge data and groundwater data. And so I really wanted to explore that. And basically what this does is it uses the shapefile for whichever watershed you're interested in. And so this is the Clackamas in Oregon. And this is Mount Hood here for those of you who are familiar with the Pacific Northwest. And from that, it all field sites for within that polygon. And so there was quite, when we were first looking at it, and if you actually look for the data, there was only one site. And so there were very few watersheds that had this daily discharge data. So ultimately that was the biggest limiting factor. And the site in Colorado, we tried multiple sites, and for some reason, I'm not sure if it's an error on their end, but the data would not download from any of the services. So that's why we stuck with Oregon. And so here I'm not going to go into too much detail with the mail script because we were all in that seminar, but we changed this to be the Oregon domain. And so this is that Clackamas watershed. And we have the SWE data as well as the precipitation data. And we got Modus and Grace. And one of our big challenges of this morning, that was kind of a last minute challenge, was learning how to fill data when there's time steps missing. So kind of that temporal interpolation if you, well, I guess we ended up filling it with nans. But anyways, how to create dimensionalities that matched within data sets. So then we pulled over that discharge data as well, which was in his original script. And then using the groundwater notebook, we were able to identify the stations and then download the groundwater data over our time period of interest. And we also have, we use the Olmo tool to get our SNOTEL data. And so we pulled the stations that fell into our domain again. And then ultimately we resampled, I think it's at the bottom. So we did look at all of these variables, but okay, I think this is the older version. Oh, no, we have it. Okay, so we ended up resampling everything to a monthly timescale. And this was one of the things that was being done for a while. One of the kind of sidebar things, when to pull our station SWE data in, actually, I'll come back to that. Okay, so once we had our monthly aggregate data, what we wanted to do was look a little closer at it and try doing some different statistical analysis. And this is, kind of ran out of time once we got to this. But some of the things, oh wait, sorry, this is, okay. Okay, so we pulled all of the data in from the monthly aggregated data. So we had precipitation, evapotranspiration, discharge. We have SWE that's extracted, this is the aggregated SWE from the DayMet product. We also have our station SWE from the SNOTEL station. And then this is the groundwater. This is the depth to the water in the well. And then we also have, this is the GRACE data thickness layer. So we went ahead and we plotted all of these together, and we're able to just kind of take a look at those. And some of the, we were also playing around with different plotting functions. So doing the hydrograph and hyetograph plot was something we were experimenting with. So here you can flip your axis to put precipitation on the top. And then you have discharge in the blue. And one thing that really stood out is the SWE that was from the DayMet data was much higher than the SWE in the station, SNOTEL station. So if you look at the SWE from, this plot here is actually showing, if you look at the SWE from DayMet, it's this turquoise line, versus the SNOTEL SWE is this blue line. And this red bar, is the red dashed line, is showing the errors. So we thought it was kind of interesting that there was a lot of variability between what was at the station versus what was at the DayMet product in the same location as the station. So that's something that we noticed. And then questions that we wanted to get at were looking at the correlation between those two SWE products. We also wanted to look at how the distributions of, so what is the error in this aggregated SWE product versus our other SNOTEL product. And then we ultimately are trying to figure out what, if we can identify a signal that from snow that shows, that's related to to groundwater recharge. So we just did some basic plotting. So scatter plotting, this is looking at, well, this is, sorry about this. This actually changed. We had some problems with our Git repo right before this started. I'm gonna just skip these. So we finally, this is what we were working on right as this, the presentation started. So this hasn't really been thoroughly looked at, but we were just trying to see if using linear regression, if any of the other variables did a good job at predicting the GRACE thickness level. And so we used the water stats code from the tutorial earlier in the week. And I'll just, so we looked at a few different variables. So here, this is SWE as it's related to LWE thickness. And there's a decent I mean, it's not a very good correlation, but one of the things that we thought stood out quite a bit was most of, or a lot of these time series of LWE basically has double peaks, and those peaks may indicate like a precipitation signal versus a snowmelt signal, and so that's something we hope to look at down the road. Yeah, so at this point, that's primarily what we did. There was one side project we worked on, or I was working on with Tony, and it was working on trying to build a database, or like a mini database, so that you could search large areas for all the stations that were in a certain watershed or on a certain aspect. And so this is what we came up with. And so the way that this works is you start with a state bound, or a state perimeter. And from that state perimeter, you could do any station that OMO can capture. This one is just using SNOTEL as its example. But using that, you can get all of the stations within a state. And then Tony has a database that has metadata for the different HUC codes. And so from that, you can add metadata to that station code so that you get the HUCs for each of the stations. And then the next steps we're working on adding DEM data. So there was a really neat notebook that Emilio shared with us from a colleague at UW. And here he had some really neat tools to work with large raster data. And basically you can, you don't have to load all of it into memory, but you can still extract information out of it. And from this, you can start with a DEM. You can get variables like slope or aspect. And then the idea was to extract all of those variables at the point of each station and add them again to that metadata you've been collecting. And then the last step was to calculate 30-year averages of different variables so that you'd have like the climatology of average temperature, average precipitation at each of those stations as well. So ultimately you end up with a bunch of metadata for all of your station data. And that's kind of neat because you can ask, I think, some pretty interesting geospatial questions as far as from here you can use that same OLMO code to then download time series data from stations of interest. So you could subset by HUC or slope or aspect or climate or mean annual precipitation. And then from there you can download the time series for the period you're interested in.